A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headaches.
If you're building anything with AI, check them out. Modal.com. Alright, we have a really interesting one today. Daniel sent us a text prompt about the way we actually get these massive AI models onto our desktops. He writes, "The typical pathway through which large language models have become available for local inference in open source communities is a big model being quantized. This is challenging because it requires the open source community to come up with inference runtimes after the fact. It also means that we are trying to run models that were never intended to be run on consumer or prosumer hardware. Have there been any models which were developed from the ground up with local inference on desktop computers in mind, in which the model was bundled with everything needed to make it work optimally, and no third-party quantization is needed? Let's try to find any concrete examples we can point to."
Herman Poppleberry here, and man, Daniel is hitting on the exact friction point of the local AI movement. We are essentially living in the era of post-production, AI, where the community is acting like a giant unpaid optimization department for trillion-dollar companies.
It does feel a bit like we are trying to fit a square peg in a round hole, doesn't it? Or maybe fitting a semi-truck into a suburban garage. By the way, before we pull the engine out of this topic, a quick shout out to our sponsor. Today's episode is powered by Google Gemini 3 Flash, which is actually the model writing our script today.
Which is a bit ironic considering Gemini 3 Flash is a massive cloud model and we are talking about the struggle of going local. But Daniel is right, the standard workflow is almost absurd when you step back and look at it. Meta or Mistral releases a model in 32-bit or 16-bit floating point format. That file is massive. Llama 3.170b is about 140 gigabytes in its raw form. No normal person has the VRAM for that.
Right, so then the community heroes, the folks like the bloke or the users on Hugging Face, take that massive file and crunch it. They use quantization to turn those 16-bit numbers into 4-bit, or even 2-bit numbers, so it fits on a 24-gigabyte graphics card.
And that is where the hack begins. Because the model wasn't trained to be 4-bit. You are basically taking a high-resolution photograph and saving it as a low-quality JPEG, then wondering why the edges look a bit fuzzy. And then, because the original model creators didn't give you a way to run it, the community has to build llama.cpp or VLLM just to make the hardware understand the math.
It's impressive that it works at all, but it's definitely not native. It feels like we are constantly playing catch-up. Every time a new architecture drops, there's this 48-hour scramble where everyone is waiting for the GGUF conversion and the pull request on GitHub so they can actually hit run on their Mac Studio.
It is a maintenance nightmare, but the shift Daniel is asking about is actually happening. We are starting to see local-first models that skip the community surgery and arrive ready for your hardware.
So, let's look at the standard path for a second before we get to the exceptions. You mentioned quantization isn't free. When we talk about these post-quantized models, what is the actual cost? Is it just a little bit of accuracy, or is it something deeper?
It's both. There is a metric called perplexity, which is basically a measure of how confused the model is by the data it's seeing. When you take a model like Llama 3.1 and squeeze it down to 4 bits using standard post-training quantization, the perplexity goes up. It loses some of its nuance. It might hallucinate more or follow instructions less reliably.
And then you have the runtime overhead. If I'm running a quantized model for a translation layer like llama.cpp, I'm not necessarily getting the raw performance the hardware is capable of, because the software has to do all these tricks to dequantize the weights on the fly during the forward pass.
Well, not exactly, but you've hit the nail on the head. The GPU has to work harder to unpack the data before it can even do the math. It's like trying to cook a meal where every ingredient is inside a vacuum-sealed bag that requires a special tool to open. It slows down the tokens per second and increases the power draw.
So what's the alternative? Daniel mentioned models developed from the ground up for this. I'm assuming that means the training itself knows the model is going to be small.
That is the holy grail. It's called Quantization-Aware Training, or QAT. Instead of training in high precision and then shrinking it, you train the model while simulating the noise of lower precision. It's like training an athlete to run in sand. If they spend their whole training cycle in the sand, they are going to be much more efficient at it than someone who trained on a track and was suddenly dropped on a beach.
That makes total sense. So, who is actually doing this? Who is the sand-trained athlete of the AI world right now?
Google is actually leading the charge here with Gemma 3. When they released Gemma 3, they didn't just dump the BF16 weights and walk away. They used QAT to release official INT8 and INT4 versions.
Wait, so Google did the quantization themselves during the actual training process?
Yes, they basically baked the compression into the model's brain. Because they did it this way, the perplexity drift, that loss of intelligence we talked about, is significantly lower than if you or I took the big model and tried to shrink it ourselves. They also optimized it to run natively on NVIDIA hardware using Tensor, RTLLL, and on mobile devices via MediaPipe.
So when you download Gemma 3 and 4-bit, you aren't getting a light version of a better model. You are getting the model as it was intended to exist on your hardware.
Precisely. It's a native local model, and because Google provides the runtime support, you aren't waiting for a community hack. It's built to work with the specific kernels on your GPU.
That's a huge shift in responsibility. It feels like Google realized that if they want people to actually use their open weights, they can't expect everyone to be a compiler engineer. But what about the really radical stuff? I remember you mentioning something about a 1-bit model a while back. That sounds like the ultimate version of this.
Oh, you're thinking of BitNet B1.58 from Microsoft Research. This is probably the most ground-up example in existence. Most models use floating point numbers, decimal points essentially, which are very expensive for a CPU to calculate. BitNet doesn't do that. It was trained from day one using ternary values, -1, 0, and 1.
1 bit? How can you fit any intelligence into a -1 or a 0?
It's wild, right? It's not actually 1 bit mathematically, it's 1.58 bits. But the point is that it eliminates the need for floating point multiplication. Multiplication is the bottleneck of AI. BitNet replaces multiplication with simple addition.
So my laptop CPU, which usually struggles with a 70 billion parameter model, could suddenly look at a BitNet model and go, "Oh, I just have to add these numbers together. I can do that all day."
That's the dream. It's designed specifically to run on standard laptop CPUs like the Apple M2 or M3 without needing a high-end GPU at all. There is no full precision version of BitNet that is better. The 1-bit structure is its native state. It's not a squeezed version of something bigger, it is the thing.
Is it actually usable yet? Or is it still just a research paper sitting in a lab in Redmond?
It's getting there. You need a specialized runtime called bitnet.cpp to run it, but the proof of concept is incredible. It's the first time we've seen a model architecture dictated by the actual physical limitations of a desktop processor rather than just make it big and we'll fix it later.
It's interesting that Microsoft is behind that, because they also have the Phi series, which seems to be their more mainstream attempt at this native local idea. I see Phi 4 mentioned everywhere lately.
Phi is a great example of the small language model philosophy. Microsoft essentially said, what if we stop trying to scrape the whole internet and instead just train models on extremely high quality textbook grade data?
The quality over quantity approach.
Right, and because they are small, 3 or 4 billion parameters, they fit into almost any consumer device. But the local first part isn't just the size. Microsoft releases these alongside something called ONNX Runtime and a tool called Microsoft Olive.
Olive? Like the fruit?
Yeah, it's an optimization tool. It basically takes the model and compiles it for your specific hardware. If you have a Windows laptop with an NPU, those new neural processing units, Olive will tune the Phi model to run specifically on those transistors.
And didn't they just launch something called Foundry Local?
They did. This is exactly what Daniel was asking for regarding bundled software. Microsoft Foundry Local is a tool where you can just type Foundry Model Run and it handles the model download, the runtime setup, and the hardware optimization in one shot. You don't have to go to Hugging Face. You don't have to choose between Q4 or Q5 quantization levels. You just run the model Microsoft built for your machine.
That feels like the Apple-ification of AI, which is probably a good segue into what Apple is doing with MLX. I know we talk about Mac Minis a lot, but their software stack seems to be doing something unique here.
Apple's MLX framework is fascinating because it's not just a runner like llama.cpp. It's a research framework that allows people to train models onto the Mac, for the Mac.
So instead of training on an A100 in a data center and then porting it to a Mac, you are building it in the backyard it's going to live in.
Well, mostly. Take a model like Small LM from Hugging Face. It's designed for devices with 4 gigabytes of RAM. When you run the MLX version of a model like that, it's utilizing the unified memory architecture of the M-series chips in a way that a generic community port simply can't. It's not converting the weights, it's treating the weights as native MLX tensors from the start.
I've seen the benchmarks. The tokens per second on MLX native models are often double what you get through a generic emulator or a non-optimized wrapper. It's the difference between a native app and an app running in a browser window.
It really is. And that brings us to the bundled ideal Daniel mentioned, the double-click AI. Have you played around with LlamaFile lately?
I have. That's the project from Mozilla and Justine Tunney, right? It's basically a single file, like an exe on Windows, or a binary on Mac that contains the model and the entire server needed to run it.
It is the closest thing we have to the MP3 moment for LLMs. If you remember back in the day, if you wanted to play a video file, you had to download codecs and special players and hope your system was compatible. Then the MP3 and platforms like VLC just made it work. Llamafile does that for AI.
What I find cool about Llamafile is that it's not just a wrapper. It uses something called Cosmopolitan Library, which allows the same file to run on Linux, Windows, macOS, and even stuff like FreeBSD. You don't install anything. You just double-click Mistral.llamafile. In your browser opens a local chat window.
And Mozilla has been releasing official versions of models like Mistral and LLAVA in this format. So it's not some random person on the internet bundling it, it's a major organization saying, here is the definitive, optimized version of this model for your desktop.
It's funny because we've spent the last 2 years as a community learning all these acronyms, GGUF, EXL2, K-Quants, and now these projects are basically saying, you don't need to know any of that.
It's a sign of maturity. We are moving out of the hobbyist in a garage phase and into the consumer product phase. But I think there's a deeper technical insight here that we shouldn't skip. When a model is born local, like BitNet or Phi, the architecture itself changes.
How so?
Well, think about the attention mechanism in a big model. In a massive data center model, you have the luxury of huge VRAM and high bandwidth interconnects. You can have a very complex attention structure. But if you are building for a laptop, you might use something like grouped query attention or multi-query attention from the very first step of training to ensure that the memory key value cache doesn't explode when the user asks the long question.
So, the model is literally thinking differently because it knows it has a limited budget.
That's it. It's hardware-software co-design. We are starting to see models where the number of layers and the hidden size of the neural network are tuned specifically to fit into the L2 and L3 caches of a modern CPU.
It's like the difference between a sprawling mansion and a tiny house. A tiny house isn't just a shrunk mansion. Every inch of it is designed to be functional in a small footprint. If you just took a mansion and shrunk it by 90%, you wouldn't be able to fit through the doors.
That is the perfect way to describe post-training quantization versus native local design. Most of our current local AI models are just shrunk mansions where we are all banging our heads on the door frames.
So, for someone listening who wants to get away from the shrunken mansion problems, what should they actually do? If I'm sitting at my desk right now with a decent laptop, what is the native experience I should try?
If you're on a Mac, go straight to MLX. Don't even bother with the generic stuff first. Go to the MLX community on Hugging Face and download a model that was fine-tuned or converted specifically for that framework. You will see a massive difference in how much heat your laptop generates and how fast the text appears.
And if you're on Windows?
Try Microsoft Foundry. It's still a bit developer-centric, but running 5.4 through Foundry is a glimpse into the future. It uses the ONNX runtime, which is Microsoft's own high-performance engine. It's significantly more efficient than running a GGUF through a third-party wrapper.
And for the "it just works" crowd, Llamafile is still the king. I keep a few Llamafiles on a USB drive just in case I'm ever stuck without internet. It's a self-contained brain in a single file.
It's also worth keeping an eye on the research coming out of the mobile space. Projects like Mobile LLM or Tiny Llama are doing some incredible work in proving that a 1 billion parameter model that is trained right can actually outperform a 7 billion parameter model that was just squeezed down.
That's the bigger isn't always better lesson. I think we've been conditioned by the cloud providers to think that only the frontier models, the trillion parameter beasts, matter. But for 90% of what I do on my desktop, like summarizing an email or cleaning up a transcript, I don't need a frontier model. I need a fast, local, private model that doesn't make my fans sound like a jet engine.
The text-in, text-out paradigm. We talked about this a few weeks ago, but the idea of using a small, local, specialist model for specific tasks is the real future of productivity. And those specialists are going to be these native local models we're talking about today.
It's interesting to think about the why behind this. Daniel mentioned it's challenging for the community to keep up. But is there a world where the big companies stop releasing the raw weights entirely and only give us these optimized native versions?
I think that's where we are headed. Look at Google with Gemma. They are setting a precedent. Here is the model, and here is exactly how you should run it. It protects their brand, too. If someone runs a badly quantized version of Gemma and it gives terrible answers, they blame Google. But if Google provides the official 4-bit version that they verified and tested, the user gets a much better experience.
It's like a car manufacturer. They don't just give you the blueprints and a pile of steel and say, "Good luck building the engine." They sell you a tuned, finished machine.
And the open source. Part of it is still there. You can still see the weights, but the usability part is finally being taken seriously by the people with the big training budgets.
So, to recap for Daniel, we've got a few solid examples. We have Gemma 3 with its Quantization-Aware Training. We have the BitNet 1-bit architecture from Microsoft, which is the ultimate ground-up design. We have the Phi series and the Foundry toolset for Windows users. And we have the Llamafile project for the all-in-one executable dream.
And don't forget the Apple MLLX ecosystem. It's probably the most practical, daily driver example of native local performance we have right now.
It's a lot more than I thought existed, honestly. I'm so used to the download the GGUF from a random user workflow that I hadn't realized how much the official channels are stepping up.
It's the prosumer shift. We're moving from the experimental phase to the "it's a tool I use for work" phase. And tools need to be reliable. They shouldn't require you to compile C++ code just to get a summary of a meeting.
I'm curious, though. Does this mean the community quantization movement is going to die out? I'd be a bit sad to see the bloke era end.
I don't think it dies, but its role changes. The community will always be the long tail. If you want to run some obscure, fine-tuned model for writing medieval poetry, you'll probably still be using community-made quants. But for the base layers of our digital lives, the models we use for coding, searching, and writing, we're going to rely on these native, manufacturer-supported versions.
It's like the difference between a custom-tuned racing car and a reliable sedan. Most days, I just want the sedan to start when I turn the key.
And I think that's what Daniel is looking for, that start the key experience.
One thing that occurs to me is the hardware side of this. We keep talking about CPUs and GPUs, but these native models are increasingly targeting NPUs. Do you think that's going to be the final nail in the coffin for the post-hoc quantization?
Almost certainly. NPUs are very picky eaters. A GPU is like a garbage disposal. It can chew through almost anything if you give it enough power. But an NPU is designed for very specific mathematical operations. If your model isn't compiled or quantized exactly the way that NPU expects, it won't run at all, or it will run slower than the CPU.
So you literally can't hack your way onto an NPU. You have to be invited.
Right, you need the official version from the developer who has the secret sauce for that specific chip. We're seeing this with the Windows Copilot Plus PCs. They only run certain models on the NPU because those models had been native tuned for that hardware.
It's a bit of a walled garden concern, but the performance gains are hard to argue with. If I can get 40 tokens per second on a laptop while using 5 watts of power, I'll take the official model any day.
It's the only way local AI becomes mainstream. We can't expect everyone to have a 400-watt power supply and a 24-gigabyte VRAM card just to use a chatbot. We need the SAN-trained athletes that can run on the hardware people already own.
Well, I think we've given Daniel a pretty thorough answer. The native local movement is real, and it's finally starting to catch up to the big model hype. It's not just about shrinking, it's about building for the destination.
It's a shift from AI in the cloud to AI in your pocket, and that requires a completely different engineering mindset. I'm just glad we're finally seeing the big players like Microsoft and Google take that seriously.
Me too. I'm tired of my lap being burned by a shrunk mansion, trying to run on my MacBook.
We've all been there, Corn. We've all been there.
Alright, I think that's a good place to wrap this one up. We've explored the rare but growing world of native local models, from Google's Gemma 3 to Microsoft's 1-bit experiments and the double-click simplicity of Llamafiles.
It's a fascinating frontier. Thanks as always to our producer Hilbert Flemingtop for keeping the show running behind the scenes. And a big thanks to Modal for providing the GPU credits that power our generation pipeline.
This has been My Weird Prompts. If you are enjoying these deep dives into the plumbing of the AI world, a quick review on Apple Podcasts or Spotify really does help us reach more curious minds like yours.
Or you can find us at myweirdprompts.com for the full archive and all the ways to subscribe.
We'll be back soon with another prompt from Daniel. Until then, keep it local.
See ya.
This episode was produced using Google Gemini 3 Flash, text-to-speech by Chatterbox.
Thanks for listening to our show, My Weird Prompts.